morning, good afternoon to all participants of this closing plenary session of the 14th Summer Workshop in Mathematics, Universidade de Brasília. So it's a great honor for me to introduce Professor Michael Scheutzow from Berlin, TU, Technical University of Berlin. Professor Scheutzow has graduated from TU Kaiserslautern, and he has spent most of his career at TU Berlin. He's a professor of probability theory in Berlin and widely recognized for his works on stochastic analysis and random dynamical systems. He has made fundamental contributions to several areas of probability theory, ergodic theory of Markov process, stochastic flows, random dynamical systems, stochastic delay equations, and non-expansive maps, and so on. And he has published more than 120 papers in mathematics, with around 1,200 citations over his brilliant career. So today he's going to explain to us the somehow remarkable phenomenon of the change of stability behavior of deterministic dynamical systems under the presence of a stochastic noise. So Michael, it's a great honor to have you here. Thank you so much for being with us. So you can start your presentation.
Okay, thank you very much, Alberto, for this kind introduction and also for the invitation to speak here in this nice summer workshop. Actually, we have snow outside in Berlin with about 0 centigrade. I will keep this talk on a very low level since we are approaching the end of the conference and probably everybody's tired. So there will be no theorems, no propositions, no lemmas, and no formal definitions, essentially just examples. Okay, so the question I will address is the following. We take a stochastic differential equation, such as the one written here on RD, on Euclidean space. W1 up to Wm are independent standard one-dimensional Wiener processes, sigma I and B are some functions. And then we wish to compare the behavior of the deterministic system with epsilon equals 0 to the system where epsilon is positive and see whether that improves or whether that improves the stability property or not. And so the question in an informal way is the following. What can one say about the relation of the long-term behavior for the deterministic system and the stochastic system where epsilon is positive? And here we think of the case where the noise is really non-degenerate, that is, it's really acting in every direction. So we're not interested in the case where the sigmas are all 0, so then the question doesn't quite make sense. Okay, and in particular, we would like to see whether the system for epsilon positive is more or less stable than in the case epsilon equal to 0. Okay, roughly speaking, I can say at this point already that almost everything is possible, depending really on the drift function B. But let's see what is possible and what is not possible. Okay, well, to start with, we should say a few words about existence and uniqueness of solutions of this equation. Of course, everybody who's in stochastic analysis or probability theory knows this kind of criteria. So under appropriate conditions, this stochastic differential equation written up there has a unique, at least a local solution. So we do allow blow up, and when I say blow up, I mean blow up in finite time, so it may well be possible, we do allow that x actually converges, the modulus of x converges to infinity in finite time. And well, there are well-known conditions like local Lipschitz conditions, for example, or locally one-sided Lipschitz conditions, which guarantee that these solutions exist at least up to a blow-up time. There's something else, namely under stronger conditions, which do not just we do not just get unique solutions for every fixed initial condition, but we can also look at the initial conditions simultaneously. And then we may be able or not to get a semiflow, which means in particular that we get continuous dependence on the initial condition. So For example, a sufficient condition for this to happen, to get continuity in the initial condition up to some blow-up time, is, for example, that B is one-sided locally Lipschitz, and we have additive noise meaning that these sigma i's are all just constant. Okay, at this point, I really want to emphasize one important point, which may be obvious to probabilists, but maybe not so obvious to non-probabilists. So what do we mean when we write a stochastic differential equation like this? We may mean two different things. Either we want to describe a Markov process, that is, we want to describe transition probabilities, the probability starting from x, what's the probability that after time t we insert set a. So these are quantities which determine or describe the associated Markov process. Or we may be interested also in the simultaneous motion of several initial points at the same time. And that is something which is not contained in the information of a Markov process. We need to know more about this. So an SDE actually can be used to describe a Markov process, or it can be used to describe a flow. And this is really not the same thing. For example, there do exist different stochastic differential equations which generate exactly the same Markov process, which have the same so-called one-point motion. Now, the transition probabilities are exactly the same, but the joint motion is completely different. So the different SDEs may generate different flows, but the same Markov process. So when we talk about stability of solutions of an SDE, we have to say, do we mean stability properties which can be formulated in terms of the Markov process associated to the equation, or are these stability properties which are described by the semiflow, for which the Markov process information does not suffice? Okay, now let us look at possible stability concepts. So this is these are possible stability concepts for an ODE from weak to strong. So the strongest one I listed here is that there exists a globally asymptotically stable fixed point. And a very weak one is that at least not all solutions blow up in finite time. And the most unstable kind of behavior I can think of is that all solutions, no matter where you start, they will blow up in finite time. So that's an extremely unstable behavior. Okay, and then there's some properties in between, boundedness of trajectories or so. Now, what are possible stability concepts when epsilon is positive and which can be formulated in terms of the Markov process? Well, we cannot expect in this case, when the noise is non-determinate, there will not exist any stable fixed point, not any constant trajectory, because the noise will kick us out of any point with probability 1. So the most stable behavior you can think of, or at least I can think of, is that there exists an invariant probability measure for the Markov process, which is even asymptotically stable. So no matter where you start, the transition probability will eventually converge to this invariant probability measure, either weakly or in total variation. Okay, here are a few weaker concepts, for example, recurrence properties of the solution. And again, there's some of the most unstable behaviors that we have blow up for every initial condition, almost surely. Okay, and now let us see how these what kind of stability concepts are possible if we just look at them. If we look at the multi-point motion, not just the Markov process. First of all, let me say that here the word stabilization in my talk will mean that there is blow up for epsilon equal to 0 for the ODE, either for all or for many initial conditions, but there is asymptotic stability of an invariant probability measure for epsilon positive. So this is stabilization as opposed to strong stabilization, which I will explain on the next slide. Okay, so this is just a copy of the previous slide, and here are possible stability concepts again for epsilon positive, but now let us look at properties which can be formulated on the semiflow, on the joint motion of all initial conditions at the same time. And here, strong stability properties are the existence of a random attractor. I said I will not give precise definitions, but let me just say what a random attractor is in an informal way. So roughly speaking, this means that if you start with a large bounded set, not just with points, but a large bounded set, then it will tend to contract under the flow, and eventually it will move like a random, like a stationary process taking values in the compact sets. Now that's what a random attractor is. And an even more stable behavior is if this random attractor is even a singleton. It's just so any bounded set will eventually move like a single random stationary process consisting of one point only. Okay. A very unstable, a very weak stability property of a flow would be that there's almost surely no blow up of the flow. Which means that if you start with a bounded set, it will remain bounded forever with probability 1. That is strong completeness. Okay, and I'll show you examples later on showing how strong completeness is related to other stability properties. Okay, and this is what I call strong stabilization. So strong stabilization means blow up for epsilon 0, and we have an attractor for epsilon positive. So that's this property here, and if even the last property holds up, then we say strong synchronization by noise. Okay. Now let me start with an example. So some of these examples are very old. For example, this one here. That's an example of stabilization by noise. So we will not look at attractors or the multi-point motion, just at the one-point motion, just at the Markov process generated by this equation. Here we have additive noise. W is a two-dimensional Wiener process, and think of the vector field looking something like this. So I want to show you an example which exhibits stabilization by noise. So the deterministic system blows up, actually blows up for every initial condition, and this is what this vector field is supposed to show you. So if you start on the x-axis, then you'll experience a growing drift, which grows, say, quadratically, so that if you start on the x-axis, the trajectory will explode in finite time. But not only that, if you start away from the x-axis, you'll have a drift towards the x-axis, and eventually you'll be caught in such a tube which becomes smaller and smaller, and guaranteeing that no matter where you start, you will always explode in finite time or blow up in finite time. Now, I did not bother to write an exact formula for the drift B here because it looks a bit complicated, but that's essentially what it looks like. Okay, that's the deterministic system. But now let us add noise. So let epsilon be positive in both coordinates, in this direction and in the other direction. And then what happens? I mean, if epsilon is positive, then it means you will no longer blow up, because if you enter this tube here, then due to the noise in the y direction, eventually you'll be kicked out of this tube. Without noise, this is not possible, but with noise, you will be kicked out. And then there's a rather strong drift kicking you back towards the origin, which will not only prevent you from exploding, from blowing up in finite time, but which will even guarantee that there exists an invariant probability measure. And that can be checked, for example, using Lyapunov functions. So I don't want to bother you with the details. So this is what one can show for an example like this: blow up for epsilon 0, and not only non-blow up for epsilon positive, but even there exists a globally stable invariant probability measure. This, by the way, doesn't say anything about the flow. So if you start with a large ball, for example, whether this large ball will explode or not, this is a completely different question. This is not. I'm not saying anything about that. Okay, see, everything is basically possible depending on how precisely you define this B. So this is a very old paper of mine from '93. There's a more recent example of my postdoc, Isabel Vorkastner. She was able to produce a very similar kind of example, which even is of potential type. So the B is the negative gradient of a potential, and she can show exactly the same properties. Okay. This stabilization by noise, I mean, destabilization by noise is not really in the title of my talk, but let me anyway give you one example showing that destabilization, very strong destabilization, is also possible. So it's again an example in dimension 2. The ST is written here, and you don't need to read this in any detail, just observe that the y process the dynamics of the y does not depend on x at all. Sorry. And this is the drift field, so just look at this. Let us start with the case of epsilon equals 0. Then, as you can see, there's a strip around the x-axis of width 2. And so here all the vector field point towards 0. So if you start with a deterministic system inside the strip, then the solutions will converge to 0. If you start outside the strip, then since the y process has this kind of drift, it will be drawn towards the strip. You cannot somehow blow up in between because there are these barriers in between. These are the places where the function h, describing the drift in the x direction, is actually 0. So there are these kind of barriers which the deterministic system cannot cross, and that's why the trajectories just stay in these between these barriers and eventually enter the strip and converge to 0. So there's asymptotic stability of the origin for epsilon equals 0. But I'm claiming that for epsilon positive, there's almost sure blow up of every initial condition. And why is that so? Well, this is due to the fact that the drift x has this quadratic term. So most of the time in between these barriers, there's an extremely strong, fast, quickly growing drift pointing in the positive x direction with this x square, and only very close to in a very small neighborhood of width, something like 2 to the minus n of these barriers, the drift becomes small and actually becomes zeros on these barriers. Now this means that the deterministic system is unable to cross these barriers, but the stochastic system is able to cross these barriers because it has this epsilon in front in the x direction. So what will happen is, just look at the y process. So for epsilon positive, the y process will eventually have excursions in this area where the y is larger than 1 and will stay there for some time. And if the process stays there for some time, it has a certain chance of blowing up due to this quadratic drift, because it will somehow manage with positive probability to cross these barriers. If it doesn't manage to cross before it returns to the strip, well, then it has another chance of doing this next time. And since there are infinitely many possibilities, eventually the process will blow up. And you may ask, how do you prove this blow up? Well, observe that the x vector field does not depend on y as long as y is larger or equal to 1. So up here, the x drift is independent of y. So what is happening is the following. So let us just look at the case where y of t is greater or equal to 1. Then we actually just have a one-dimensional stochastic differential equation describing the motion parallel to the x-axis. That's this constant 1 here. And then you can actually, there's a well-known criterion called Feller's test of explosion, which tells you whether solutions to this equation blow up in finite time or not. So this is Feller's test. You just need to check a certain integrability condition on this function v here. And if this thing is finite, that is, if h tends to be quite large, which it is if it's quadratic, if this is finite, then there's almost sure blow up for every initial condition. And this is actually what is happening here. So you can check for the function h, at least if you interpolate it in the correct way, this will be finite because this h is small only on these on the union of these very small intervals around these barriers, which together have a finite Lebesgue measure. Okay, so this is destabilization by noise. Now let's look at the question whether there is actually stabilization by noise in dimension 1. So was it necessary to have an example in dimension 2, or can you also find examples in dimension 1? And I'm claiming no, you cannot. So we now look at a one-dimensional STE, like the one written here, again with additive noise. We assume that the deterministic system blows up. So say B is locally Lipschitz. So for epsilon equal to 0, we want to blow up and say, without loss of generality, all solutions blow up to the right. Then it means B is positive. And then you all know that if you take the inverse, this integral here, this will be finite for every C. So we get blow up for all initial conditions if and only if this integral is finite. Okay, now one can ask, under this condition, can we stabilize the system? So if we add noise in this way, additive noise, is it possible to at least to prevent blow up, maybe even to get existence of an invariant probability measure? And I'm claiming no, this is not possible. And so this is the question which I just addressed. No, it's not possible, and it's even true no matter what we do, no matter how we define B, as long as it satisfies this condition. For every epsilon, the solution of the SDE will still blow up in finite time, almost surely. And again, you can check this by Feller's test. I mean, this is just a basic exercise. So Feller's test, just remember that this is Feller's test. So if this is finite, then the system explodes. So the question now is, if the inverse of B satisfies this integrability condition, so that the deterministic ODE blows up in finite time, is it then possible that this is actually infinite, meaning that the system does not blow up? And I'm claiming, no, this is impossible. It will always be finite. And to see this, you can employ an integral inequality. So here is some integral inequality, which you may not have seen before. It's true in great generality. So if G is any, say, measurable, for example, non-negative function, then this integral inequality holds. And what does it say? Well, now if you want to apply it here, so we want to apply this integral inequality to check if this is really finite, and I'm claiming it is finite, if we define G of Z just to be x of minus 2 divided by epsilon squared times Z, G is just this exponential function, which of course is integrable, so this is finite. And we also assumed that this is finite, so the product of these two numbers is finite, so the left-hand side is finite, but the left-hand side is the same as this left-hand side, so this is finite, so there's blow up. Okay, so there's nothing we can do, whatever B is, as long as it satisfies the condition that this is finite. The random system, the SDE, will blow up. This integral inequality, it's not very hard to prove, so this is a reference from some paper from 1995, I think it was in the Journal of Mathematical Analysis and Applications. Okay, so stabilization by noise in dimension 1 is not possible. At least it's not possible if we use additive noise. But what about multiplicative noise? Okay, so there are two possibilities to interpret multiplicative noise. Either we look at this Ito equation, again in dimension 1, x is one-dimensional, w is one-dimensional, or we can use a Stratonovich integral here, and then we can ask again, if the deterministic system with epsilon 0 blows up in finite time, can we then find some function sigma and some epsilon maybe, such that the solution of this equation will not blow up and maybe even have an invariant probability measure? And we can ask the same question in the Stratonovich case, and actually the answers turn out to be completely different depending on whether we mean this equation in the Ito sense or in the Stratonovich sense. So for the first equation, for the Ito equation, we can produce extremely strong stability. So no matter what B is locally bounded, can increase like mad. So in particular, the deterministic system may explode. Still, we can find a sigma which increases even more quickly than B, which is even C infinity, if you like, so that it prevents blow up. But not only that, it even has the associated Markov process even has an invariant probability measure for every epsilon positive, and you just need to define sigma, choose sigma to grow even faster than B, and then you can apply these usual criteria for existence of an invariant probability and blow up to check that this is true. So that's again an easy exercise. However, in the second case, so if we take Stratonovich, then the answer is completely different. So if there is blow up for epsilon equal to 0 for all initial condition, then that automatically implies that this will also blow up. no matter how we choose sigma. Again, you can transform this to an equation and then check the Phillips test. So this is again an easy exercise. But it may be quite interesting to see this huge difference between the E2 and Stratonowicz interpretation concerning stabilization by noise. Okay, now let us finish this first part about stabilization, and now we look at the question of strong stabilization or synchronization. So now we compare the deterministic equation with the flow generated by the stochastic differential equation. So these are now properties which are not fully described by the Markov process. Okay, so the question is the following. Consider a two-dimensional SDE, which blows up for epsilon equals 0, either for all or at least for some initial conditions. And now let us also assume that we have stabilization, namely there exists a unique invariant probability measure for every epsilon positive, which by the way is automatically globally asymptotically stable. That's a general theory for at least for non-degenerate equations. So the question of what can its flow look like? Will the flow admit a random attractor? Will it maybe even synchronize? Or could it be that the flow is actually, the flow itself blows up? And that is indeed possible. So there are two possible answers. So first of all, there exist examples where in spite of the fact that the Markov process has an invariant probability measure, the flow still blows up, so it's not strongly complete. There will exist initial conditions which will explode when epsilon is positive, explode in finite time. I'll show you an example in a moment. And then I'll show you two examples which exhibit quite a different behavior where there exists a random attractor and in one case even strong synchronization by noise holds. Okay, let's first go to the first example. So just 3 examples remaining in the talk. Okay, this is a two-dimensional stochastic differential equation of this very explicit form. This was suggested by Jonathan Mattingly several years ago. If we first look at the case where epsilon is 0, so we just look at this ODE, then you can see easily that if you start on the positive x-axis, then y, of course, initially is 0, but y remains 0 as long as epsilon is 0. So if you start on the x-axis, you'll remain on the x-axis, then y is 0, then you have this quadratic drift, which means that you'll blow up in finite time. Okay, so you don't get blow up for every initial condition, but for every initial condition of this particular kind. Okay, so this is obvious. The next thing, which is not quite so obvious, is that for epsilon positive, there exists actually an invariant probability measure of the corresponding Markov process. And that was shown in a paper by David Herzog and Jonathan Mattingly in this paper, which appeared in EJP in 2015. It's a very long paper. It even has 2 parts, together more than 100 pages. They do not just look at this equation, they also look at other equations, but this is some of the simplest equation which they are treating and which shows the kind of effects they want to show. Okay, I'll show you the drift vector field of this on the next slide. The claim is that for every epsilon positive, it is not only true that we have stabilization by noise, so there exists an invariant probability measure, but okay, it's this we know, but actually still the associated stochastic flow. So if we look at all initial conditions simultaneously, there will be blow up of some initial conditions. So that's maybe a very easy example of a stochastic differential equation whose one-point motion, whose Markov process is stable because there is an invariant probability measure and all transition probabilities converge to it. Still, the corresponding flow is not strongly complete. There exist random initial conditions which will blow up in finite time. The reference is this paper together with my former student Matti Leimbach. And just as a reference, there are 2 other papers related to lack of strong completeness. I think David Elworthy was the first person to find explicit examples of that kind, but these were not of these. In that case, the deterministic the system did not blow up in finite time. And that's a paper with Shumei, which is actually a two-dimensional SDE, which has no drift, so there's no drift at all, but there is a diffusion, non-trivial diffusion, which is, however, bounded, which is infinity, so you would expect this to be nice. But still, there's no strong completeness. There will exist initial conditions which blow up in finite time, in spite of the boundedness of the drift and of the diffusion. But the point is here that the diffusion coefficient really oscillates like mad. So it's infinity, but it's not globally Lipschitz, and that's somehow what makes it possible to construct examples which are not strongly complete. But the following example here is easier. So this is again the same equation as before. This is the drift vector field. And what you can see is, or what you can easily check is that in the deterministic case, when epsilon is 0, then of course on the x-axis we know this will blow up. But if you start away from the x-axis, then the trajectories will move around on a circle, which is tangential to the x-axis and where the center is on the y-axis. So in particular, it will not blow up, and it will actually converge. So all solutions except for these will converge to the origin. Now, if you add noise, the picture becomes different. I mean, as before in these cases with these tubes, the process will be kicked away from the x-axis and will thus not blow up. But I mean, the question is now, does there exist an attractor? So what happens to the image of bounded sets? And here's the way you can think about this here. So if we start with all these blue points at time 0, and then we move these blue points under the flow. So we solve the equation with all these initial conditions simultaneously. Then after some time, maybe this is up to this red curve. Typically, actually, something different will happen. So if the x value of this blue line is sufficiently large, then it's very likely that some points up here will cross the upper diagonal, and some points down here will cross the lower diagonal, so that we get a connected red line, which will stretch from the upper diagonal to the lower one. What does that mean? Well, every fixed point, every fixed blue point will somehow eventually either cross up there or it will cross down here. But since this is connected, there will exist one point at least which somehow cannot make up its mind whether it wants to cross this diagonal or this one. So it will stay reasonably close to the x-axis. Thus, it will experience a strong drift in the positive x direction and will actually blow up in finite time. Now, so one of these points, at least when the x value is very large, then with high probability there will exist a point, but a random point, and random means it will depend on the future of the noise. There will exist a random point which will actually blow up in finite time. So that means the flow is not strongly complete, in spite of the fact that there exists an invariant probability measure. Okay, in fact, in this particular example, it's unimportant whether W1 or W2 are Brownian motions. We can choose any continuous process or also continuous deterministic functions. It will show the same effect. For example, if you choose W1 and W2 to be equal 0, then we're back in the deterministic case, for which we know that there is an explosion on the x-axis. But the same is true for any continuous functions, W1 and W2. Yeah, okay, so this is somewhat a bad example, so, but also quite interesting because, okay, the Markov process has a unique invariant probability measure, which is globally asymptotically stable, but still there's not only no attractor, but even some points blow up in finite time. Okay, but now let us go to two examples of strong stabilization where we do get an attractor for the case of epsilon positive. So this is an example which again goes back to Jonathan Mattingly from Duke University. It's a two-dimensional SDE written in polar coordinates. So r is the radial part, phi is the angular part, and it's of this particular form written here. In this case, we only perturb the angular part and not the radial part. I don't think it would be a problem to also perturb the radial part, but proofs become a little bit easier if we don't allow noise here. Okay, so strictly speaking, there's not additive noise in the XY plane, it's just additive noise in the angular variable. Okay, and then W, V, and gamma are some parameters satisfying certain conditions. What is important here is that V is strictly larger than 1, which means the following. So there's a drawing of the drift vector field here for a certain choice of parameters. So what you can see here is if you start with pi over 2, the angular part is pi over 2, then the cosine is 0, so there's no drift in the angular direction. When epsilon is 0, the phi will stay pi over 2. But then this is also 0, and you get this RT to the V. V is larger than 1, so you know there's blow up. If you start exactly with phi equal pi over 2. But there's not only blow up in this case. When epsilon is equal to 0, actually all solutions blow up, possibly with the exception of the origin where this is not really well defined. So if you start away from this line phi equal to pi over 2, then you see there's a very strong drift of the radial part to 0. Then there's this dangerous region, this red region, and in this red region actually all trajectories will blow up in finite time. So this you can check. It's not completely obvious, but it's also not hard to see this. Okay, but what happens if epsilon is positive? When epsilon is positive, then actually, since this red area becomes smaller and smaller as you go up, the noise will again be able to kick you over this red region. So just by random fluctuations, not by the drift, but by random fluctuations, you'll be kicked over this red region, and then you'll have a drift which will bring you into this blue area where the radial part really goes down considerably, and then you can show that the effect of going down here is much stronger than the effect of going up in the middle. So when the radial part is large, you'll actually have a tendency for the radial part to decrease, and that's why you get an invariant probability measure. But I'm claiming that not only is there an invariant probability measure, but there's even strong stabilization. That is, there exists a random attractor. So large balls, for example, or large bounded sets have a tendency to contract. So if you start with a ball of radius r, and r is very large, then typically after some time, this large ball will become much smaller under the influence of the flow, and eventually it will move like a random process taking values in the compact sets, which is stationary. Okay, now how can you prove existence of an attractor? This is a sketch of the proof. I can try to check this. So for an attractor, as I said, we start with a very large ball, say. So RK is a large number, it's the radius, and these red points are just points on the sphere around the origin with this radius. And we want to see how this red region, this red line, how does it evolve under the flow? And well, it might go up or it might go down. So let us simply define two stopping times. The stopping time τ1 is just the first time when one of these red points hits the next level, rk plus 1. And the stopping time τ2 is the first time when all these red points fall below rk minus 1. And then one can show, by looking at the equation more closely, that it's actually quite likely that τ2, this time to reach the next level below this, is typically much smaller, or it's much more likely that τ2 happens before τ1, so that this red line actually has a tendency rather to become smaller than it has to become larger. And that's how from that you can deduce that there is a random attractor, that large sets tend to contract. Okay, so this is full proof of this is contained in a paper with Matti Leimbach and Jonathan Mattingly, which will appear in Prof, pure and applied functional analysis in a few months, I hope. This is in a special volume on the occasion of Peter Cluiden's 70th birthday. Let's now go to the final example. So maybe I'll go back here to, so there may be things you might complain about. First of all, the noise is not completely non-degenerate, so we don't have any noise in this direction. Also, the noise is not additive. Also, blow up for epsilon equals 0 doesn't happen for all initial points, just for all initial points other than the origin. And also, we don't get that the attractor as a singleton. We just get the existence of a attractor, and actually in this example it's clear that this attractor cannot be a singleton. So there are 4 slight drawbacks to this example, and we can ask ourselves, is there an example which doesn't have any of these 4 drawbacks? And yes, there is, and it's this example, for example. Okay, so it's again a 2-dimensional ODE with now this time really additive noise in usual Cartesian coordinates, not in polar coordinates. And what I'm claiming is the following, namely, for epsilon equal to 0, there's blow up for all initial conditions. Let us first see why this is the case, so that's indeed easy. And then we'll say something about the case epsilon positive. So assume for the moment that epsilon is 0, so there's no noise here. What will happen? Well, you see that the y process here is autonomous. I mean, it doesn't depend on the x at all. So we can somehow solve the y equation first and then plug it in here. And you see that y, when epsilon is 0, this y process has a negative drift here, so it will definitely converge to 0 as t goes to infinity. But not only will it converge to 0 as t goes to infinity, it will even converge to 0 in finite time. That's due to this square root, which means that we cannot solve this equation backwards. But in the forward direction, this is perfectly okay. This is a one-sided, the drift is one-sided Lipschitz, so there's no problem about existence and uniqueness of solutions, neither for the case epsilon 0 nor for the case of epsilon positive. So don't be too worried about this case here. There's a minus sign in front, and that makes everything nice. So y will hit 0 in finite time, but once y hits 0, then this term is 0. Well, then first of all, y will remain 0 forever. And this term is 0, then you get this quadratic term here, and even if x is negative, you have this +1 here. So this will blow up in finite time for every initial condition when epsilon is 0. So this is indeed easy. Okay, but the price we have to pay, I mean, I don't know any example which is of the kind I want to show here, where this is really globally Lipschitz or even locally Lipschitz. So this is not locally Lipschitz. Okay, but I think that's okay, because these are solutions are still, well, they exist and are unique for all positive times. You cannot solve them backwards, of course, but that's not what we are concerned about. Okay, now let us look at the case where epsilon is positive. And now what I'm claiming is this is really noise-induced strong synchronization. So I'm claiming that if epsilon is positive, we do not only get an invariant probability measure, which is globally asymptotically stable, we even get an attractor. And not only that, we get an attractor which consists of one single point. And now let me write down here what I really mean by synchronization, by strong synchronization. So we look at this flow, the solution map associated to this equation. We take a bounded set B. We start at time minus s, where s is very large, so in the remote past, we start with this set B. We map the set B under the flow up to time 0, and so then we get some random bounded set, and we compare it with this point here. And then the claim is that the Hausdorff distance of these two sets will converge to 0 in probability as s goes to infinity. And so for large S, it's very likely in particular that the image of the set B will be contained in a small neighborhood of this random point at time 0. Okay, so this is the equation again, and now let me indicate what one has to show in order to prove strong synchronization. Now there are a number of points here which I will list, and there's some color coding here. So the red things are things we need to show, which are not completely obvious. Green things are which may also not be completely obvious, but which follow from general theory. And blue statements, I'm claiming, are clear or at least easy. So the first observation is that if we just look at the y process in isolation, so epsilon is positive, and we just look at the y process, that's a one-dimensional diffusion. It has a reasonably strong negative drift pointing towards the origin, so that an invariant probability measure exists. We have additive noise, and then by general theory it follows that this actually synchronizes, because this is a one-dimensional diffusion. It's order preserving, so it has no choice other than to map intervals asymptotically to points. So even a large interval at a large negative time will contract to a point at time zero, a random point. And this random point will be denoted by B of omega. So this is the attractor of the y process alone. So this is a real valued random variable. Okay. The next thing, I'm claiming that this SDE is weakly complete. Weakly complete just means that for every initial condition, there exists a global solution. While strongly complete means that the flow doesn't explode, weakly complete just means that solutions, individual solutions don't explode, which is a weaker concept. Okay, so we assume that this is true and that it admits an invariant probability measure mu. Now one can check this. Actually, we don't need to check this right now. It will follow from other results later on, but this is something, let us just assume for the moment that we know this. Then again, from general theory, it follows, since this is noise is additive, it follows that the measure is unique and it's globally asymptotically stable, no matter where we start. All transition probabilities will converge to mu, actually in total variation. Okay, now there's something called statistical equilibrium. Again, that's general theory. So if we take this particular invariant probability measure of the Markov process, and we map now not the set, but we map this measure, this probability measure, up to time zero as before, then we get a random measure at time zero. This exists, that's general theory, some martingale convergence theorem. This is often called statistical equilibrium. It's a random measure, somehow describing the image of this invariant measure at time zero under the flow, started in the remote past. Okay, now what does this measure look like? Well, we know that y synchronizes. So y synchronizes means that if we take the measure mu, say, at time minus infinity, then the image of this measure will be squeezed somehow by the process y, and it will contract to something which is parallel, a random parallel to the x-axis. So the support of this measure, we don't know whether, well, it's a probability measure, but we don't know whether it has compact support or not. It may be extended in the x direction, but it cannot extend in the y direction because the y synchronizes, it compresses everything to this random variable. So the support must be contained in here. This is now fairly clear. But not only is this true, we want to know more. We want to know whether the support is a singleton. And indeed it is. That's again, maybe not clear, but at least easy, that the support is actually just given by a single point. Let me indicate why this is so. So assume we take 2 points on this set here. So 2 points, maybe one has a very small first coordinate, the other one has a very large one. And then we just observe how these 2 points, which have the same y value, the same b of omega, how the distance of these 2 points changes. And since we know that mu is globally asymptotically stable, it means in particular if we take 2 points, even though they are random, but the argument still applies. So if we take 2 points, asymptotically, their distributions converge to the same measure. And since they always remain in order, so the one starting further on the right than the other one, they have no choice than to converge together somehow. So the distance will converge together. So this measure xi will also be compressed in the direction, in the x direction, meaning that actually the support is not just this whole set, but it's just one random singleton. Okay, now this doesn't yet solve our problem. It doesn't mean that this is an attractor, but what it does mean is that it's a point attractor. So this random point is then, by general theory, a point attractor. And this phenomenon is also called weak synchronization. So a point attractor is just an attractor which does not necessarily attract bounded sets, but it attracts individual points. So every individual point, as you take it to minus infinity, you map it under the flow, it will be very close in a very small neighborhood of this random point. Okay, so at least we get a point attractor, but we're not happy with this. We want more. We want to show that this is actually a set attractor. It also attracts bounded sets. And this is not completely obvious. And one can probably even find very similar examples as to this one, where all of this is true, but there is actually no attractor. Or there may be an attractor, but it's larger. Okay, but I'm claiming that if this flow admits a random attractor A, if it does, it's not clear whether it does, but if it does, then it has to be the same as this point attractor, and that then we are done. So once we can show that it admits a random attractor, whatever it looks like, then it automatically has to look like this. And I decided not to try to explain why this is true. It's a similar kind of argument as these arguments for the psi that bounded sets are somehow contracted, but one has to be a little bit careful at some point. Okay, now if you want to read these green things to see where this is written, there are two papers together with Franco Flandoli and Benjamin Gess in 2017 called Synchronization by Noise or Synchronization of Order-Preserving Systems by Noise, and there you can all find these green statements. This does not contain this example, of course. This example is really new. Okay, I'm not quite sure whether I mentioned this, but let me just, yeah, this example is really, as you can see here, it's really very new. So I didn't mention this example in the abstract because the abstract is from last year. Okay, it's not even on the archive, the paper, but it will hopefully be on the archive in about 2 weeks. Okay, so as a final step, let me try to indicate how one can prove that there is really a random attractor. And that's very similar to the proof I showed you before. So the only direction which is somewhat critical is the positive x direction, because the deterministic system blows up in the x direction. Okay, so what we can do is, again, we can look at this red line. We can take two neighboring lines, say for x equal n minus 1 and n plus 1. And then we can, again, define these two stopping times. Say tau 1 is the first time when one of these red points hits the next level, and tau 2 is the time when all these red points for the first time are to the left of this line. And then again, one can hope to be able to prove that the probability that tau 2 happens before tau 1 is much larger. It's much larger than 1/2. And then, of course, everything is clear, because that means some of this red line tends to move to the left, and that means somehow large bounded sets tend to become smaller. There's no problem in the other directions here, but the only critical direction is this one here. And why is it true? Why does this have a tendency to move to the left? Well, the reason is you can define a small neighborhood of the x-axis depending on n. And then we know that inside this area here, we have a rather strong drift to the right, like x squared. However, outside of this area with this minus x to the 7th part, so there's a very strong, even stronger drift to the left. And then one can show that, first of all, this y process, it will spend very little time in here. So the y process will be kicked out of this area very soon. It will spend, even in short times, it will spend very little, very small proportion of time in here, no matter what the initial condition of y is. And that means that the solutions experience much more of this very negative drift than they experience of this positive drift. So all in all, all points on this red line will rather have a much higher probability of hitting the next smaller line than they have than even one of these points has to hit the next line. And that's how one can prove actually the existence of a random attractor. So I guess my time is up. Thank you very much for your attention.
So thank you very much, Professor Scheutzow. We open for questions. So if you have any questions, so please write on the YouTube chat. We have one question. Yes.
Okay, you can see it here. So is there any interest in replacing the constant epsilon by epsilon of x? Which is really something like saying, I mean, we could also then take sigma of x, right? So this would not be additive noise, but kind of multiplicative noise, but a small multiplicative. It's similar to epsilon times sigma of x, right? So I think it's basically the same question as multiplicative noise multiplied by small epsilon. Yeah, there is some interest, certainly. I mean, in the one-dimension case, I addressed this question whether sigma was x-dependent. Actually, to find these examples of very strong stabilization, it was more challenging not to allow this. So we really wanted to have epsilon constant, just additive noise, because we already know more or less that for Ito equations, when we allow multiplicative noise, then anything, I mean, any stabilization can happen already in dimension one. So maybe this is not quite so interesting in my view.
Another question of Leandro.
Is it possible to compute the expected values? Okay, that's a good point. So in this last example, we have this random point, this A of omega, B of omega. It's certainly possible to say something about the distribution of this. So, for example, I mean, one thing is, that again follows from general theorem. Once we know the invariant probability measure, mu, of the equation, then somehow the distribution of this is distributed according to mu. So we know this is kind of a disintegration of the probability measure. So in particular, we can determine, if we know mu, for example, we can determine the probability that, say, this point is contained in a certain sector. So this follows from the fact that this is distributed like the invariant measure.
Yes. Any more questions on the YouTube chat? Yuri.
And it depends on the size of epsilon of the properties of the attractor. Yes, there certainly is. For example, typically what you would expect is that the smaller epsilon is, in these examples where we blow up in the deterministic case, for example, in the positive x direction, you would certainly expect that the attractor moves out, is very concentrated on very large x values when epsilon is very small, and that it will actually converge in a reasonable sense to the to plus infinity or so. And in some cases, one can prove this actually. I haven't tried this for this last example, but it should be. That's what you would expect.
Yes. So I have a question. Can you come back to the slides on one-dimensional stabilization for SDs?
Let me see if I have to go back to the slides. So once again, which slide?
Stabilization for one-dimensional SDs. Additive noise.
One-dimensional SDs, okay.
Yes, at the beginning of this.
You mean this one or the one before? This one?
No, before. Yes, before.
This one?
Yes, that's right.
Okay.
So in the one dimension, it's the fact is not. It's not true that if you add the noise, then you have a stabilization, right? So it's
right. If you add this kind of additive noise, cannot possibly stabilize the equation. That's right.
yes. So I was wondering about if you work with more regular noise in some sense, such as, let's say, fraction problem motion when the exponent is
Okay,
bigger than 1/2. So my question is it any results in this direction?
that's a good point. I never thought about this. I should take it. Of course, these arguments don't apply because these Feller's test, which was used here, this is specific for Brownian motion, and it does not
Yes.
work for fraction Brownian motion or any other noise. Um, so I would be surprised if this could be stabilized by, say, fractional Brownian noise, but I really haven't thought about this.
Yes.
It sounds like an interesting and natural question.
Yes, because when the Hertz exponent goes to 1, then would have a different regime, and there is no noise. Yeah, it sounds interesting to see what happens.
Yeah, I would still think that this will not help. That if you take, say, a fraction Brownian motion of whatever Hurst index, it will still blow up, but I'm not sure.
Yeah. Okay. So, any more questions on the YouTube chat? Okay. So, I'd like to thank you. It was a great honor for us, Professor Scheutzow, to have you here. And thank you very much for your talk. It was a very nice talk. And I would like to thank all the participants for the workshop, summer workshop in mathematics. This is the closing session. Thank you, all the participants and the staff, the team, and the speakers, especially the speakers. And we see you next year for the summer workshop. Thank you very much.
Okay, bye bye.
Bye bye. Bye bye.